So we are coming to our MATLAB live session. It's 25B of our course on mathematical methods on signal processing. And the question was, what is the Gaba command doing? Well, you have seen there are lattice points. Each lattice point corresponds to a certain time frequency shift parameter, and they are coming in a natural order. And so if we are having this collection, you can expect, and now you should see it in a moment, that in this collection, the first three elements are just a Gauss function. And then a Gauss function modulated, seems to be very slow, and then modulated more and more as you go down in the first column. Yeah, okay, so here you see, for example, element, yeah, you're taking every 25th element from the Gabor family. So what you should see here is the first 8 Gabor elements. So maybe it should not be displayed so quickly or so. Oh yeah, here is something that nice. So this sorry, it's a bit, yeah. So this plot was the plot, this multiple plot. I will insert it in the PDF file, where you would see that each building block has a concentration in time frequency plane, and that would be exactly at the point with the corresponding number. So if I'm looking at this element here, yeah, maybe I'm taking the last plot here. I'm doing here a section break so that I can repeat it. I would say we mark in our particular environment, we mark the position of the axis. So the central position would be the time frequency shifted element here. But if you want to, for example, if you would like to see an element which is a Gauss function, rod mode of the Gauss function, I don't know, time shift 30, frequency shift 50, to see that we can distinguish it in the plot, then it would go to the right by 30 pixels. So the center would be at roughly 30 pixels to the right and going down 50 pixels. Of course, I can take more than 1/2. So I could go, I don't know, 350. And you should see that you have at the same position a Gabor atom, which is in musical terms a very high frequency, but it's already so close that it comes back from the other side. So if you would do this, if I go from 30 in the time shift to this, and maybe I don't take such a big frequency shift, then I would, oops, sorry. Then you would get a plot which is at 130 time shifted in frequency. Now, I cannot do it spontaneously, but not long ago, just last year, I was trying to do a little composition. So I was taking not Gauss windows, but Henning windows, which are of the length of 1/10 of a second. And I was kind of programming in MATLAB a very simple synthetic piano, so to say, which was playing a melody. And then I was taking through the microphone the recording, and it really looks like the computed one. So that's a very important aspect actually of this whole story, that what you get from a piece of music with no ground truth is very much the same as what you would compute directly from the data without any sound interference. And that's, I think, a great experience to be able to compute. Okay, so if I have now a matrix with 721s, be they regular or not, then I would go through this matrix in MATLAB order. I would choose the indices, and for each indices, I have a time and the frequency offset. I would compute it, and I would add as a next row this to this element here. So this is how the Gabor basic matrix is done. In the product matrix, I know that I have always the same modulation. So all of them are modulated in the same way, whether I'm in the first column, second or so, and that allows to make it faster. And the other one, you really do kind of rod mode one after the other, but you are free to do it in a completely irregular way. We could also do it demo with irregular Gabor families, but that's not for today. Okay, now the next thing I would like to recall to you is that for random matrices and random vectors, and that's what I mentioned already earlier, the scalar product is just x with y square, with y prime. So the natural order of things in the scalar product are also the natural order in MATLAB. That's why I like it. And to show that it's really the same as the scalar product in naive way, I'm taking x1 plus y1 plus x2 plus y2 conjugate, sorry, and so on. That's the definition of the scalar product. And you can check for random vectors, it's the same. So it's really just the standard scalar product. Why do I repeat this remark? Because for me, by doing right multiplication with the Gabor family, I create from row vectors, from the given signal that you would give me, a collection of 720 coefficients. So we have a collection of 720 Gabor building blocks, and we take those scalar products. Now, we can also take now from this coefficient set a synthesis. We resynthesize, and that's exactly what this frame operator is doing. It's treating the system of vectors as if it was an orthonormal system. You will say, I take the scalar product with respect to a vector number 5, 6, 7, and so on, and that's my amplitude for a vector number with the corresponding number. Now we're doing the same thing, and that's why this so-called Gabor frame operator is nice, and one can show that the null space of this operator is the same as the orthogonal complement of the linear span, but we are assuming, or we hope, that our vectors are spanning the n-dimensional signal space. So in this case, this would be invertible, and that's actually the definition of a frame in an abstract Hilbert space. One would assume that one has this frame operator, and this will be done in the abstract course again, which is just the n by n matrix. So you should look at the format here, the size, yeah, it's clear. I mean, G is a format 720 by 480. So the transpose format is 480 by 720. We multiplied with 720 by 480. Now, it has a certain structure, and I have already indicated this earlier on, but the simplest way is, where are non-zero entries? And the answer is, it's coming in here. So it's concentrated on the main diagonal, and maybe I should just tell you and show you something different. And the claim is that this frame operator is commuting with the time frequency shifts that we have. So we have our operator, and we can now, well, maybe I'm doing a time shift. TA is the time frequency matrix, which is format N, A, and 0. And the modulation by B is our time frequency shift matrix, pure frequency shift, 0 time shift, and B frequency. So these are the two building blocks that help us to move around. And now I'm checking whether this frame operator, which I have called the frame operator coming from the Gauss atom A, the lattice constants AB, multiplied from the left or from the right with TA, are the same. So I'm just forming ordinary composition of operators or matrix multiplication. And of course, I will do the same thing with SGAB with modulation operator in one or the other order. Let's see what we get. And you see we're perfect fine. So numerically, it's clear, and that's also what you can prove. So roughly speaking, the good thing is that if you are getting a Gabor operator coming from a group, so it's essentially these operators, the two time shifts are generating the whole group. So how do you get from one lattice point to another one? Maybe you're doing a multiple of the time shift A, maybe you're shifting by 60, but of course shifting by 60 is also commuting. So it's enough to check these two directions, and you will get the whole thing. So of course you can combine it. So every lattice point in our lattice is a time shift, frequency shift operator, and they all commute with our Gabor operator. And then to come back to this picture, one can show that the invariance under time shift means that every matrix is constant, in sidediagonal. So we have an A periodic function in the diagonal. So that means not aperiodic, but periodic with period 20 in our case. Actually, the main diagonal, it can be described. That's maybe something we can do. Is, yeah, I would like to show you that the main diagonal is obtained by periodizing the G squared. So I would say, let's do the SHA-A is zeros of length n. So it's, and more to make it direct comp, and I put into this vector a distance A from 0 to n, more or less, put a 1. And so what is SHA? Maybe I'm saying G squared periodic is, I convolve it, so well, I know it's real, so maybe I take the real part of IFFT of, on the Fourier transform side, I know it's a Gauss, but I do it. And this would be the Fourier transform of SHA. So of course I could say, this is a Gauss function, this is a Dirac comp at distance n over A, which is 24, but we are really doing it. And so my claim is that the main diagonal of the Gabor frame operator with the product lattice is the same as the Gabor squared periodic. Let's see, I hope I didn't make any mistake. Let's run this little experiment. It's somewhere here. The problem is I don't see now where we are. It's okay, sorry, it must be after this plot. Yeah, I think it was correct, but or it should be correct. If not, I will check it once more. Maybe I shouldn't lose time. Now, let me go here. Yeah. Now, what one can do with, I mean, how can one get the coefficients? And I should remind you that whenever you have a redundant family, so we have 720 vectors in a 408-dimensional space in our example, you can represent a vector if these vectors are at least spanning the whole space. And they are doing this in a very nice way in many, many different ways. So there is clearly a null space of dimension 720 over 480, or because we had redundancies 3 over 2, the redundancy is 1/2. So it's 240-dimensional null space. So the many, many representations. The question is, which one is the best? And the answer is, solve the minimal norm least square problem, or take the space of all possible solutions of the inhomogeneous linear equations. Maybe you remember this part of linear algebra, and it's a specific solution plus all the others of the homogeneous case. So it's an affine subspace of our 720-dimensional space of all possible coefficients. Now, in this affine subspace, there is a unique element of minimal norm, and that's what the pseudo-inverse is giving you. And in our case, we are getting it in a very nice way. We just have to invert the Gabor frame matrix, which we have seen is a very nice matrix. I'm doing it from the right, just because you remember me. And we look at this, and now we see a plot of the function, the Gauss function. It's Fourier transform, the dual thing, which was the Fourier transform of the dual. So this is what we are going for. Sorry, it's a bit confusing now. Yeah, so we are doing the inverse, and here I'm just checking, and you have it on the right hand side. I have done it beforehand, so you can check it on the PDF file, that the dual one can be either obtained by taking the pseudo-inverse of the family, of the Gabor family transpose conjugate, which is the same as the system of getting the cheapest coefficients. And then the pseudo-inverse can be used in two different ways. Actually, this is not a very good trick. It should be, if you would give me the scalar product, so I'm repeating this experiment, if you give me the scalar product with the Gauss family, so that would mean you're sampling your short-term Fourier transform at those lattice points, then you could resynthesize your family using the dual window for the atoms. Or the first one would be, I'm asking you to provide the minimal norm coefficients for a Gaba family, and then I would get it by taking the samples of the short-term Fourier transform with respect to the dual window. So we have many different routines to compute the dual window in a very efficient way. Just recall or observe that this Gabor frame matrix is a very well-structured matrix, and it's a positive definite matrix. So some of the algorithms work very well for positive definite matrices, much faster than for general matrices. And what the comment that you find about Gabor analysis in the early literature, it's a non-orthogonal system. I mean, clearly a system cannot be linear dependent and at the same time orthogonal. So therefore, inversion or representation is complicated. It's just at the end nonsense, because it just says, well, if it would be a very general matrix, everything would be okay. But we have seen it's a matrix with a lot of structure. There are only few sidediagonals which are occupied. And this is due to the fact of change of the modulation, whereas the aperiodicity is coming from the shift invariance, from the commutation with the TA. So we have a lot of structure, and it's only a question, or it's not only, but it turns out that all the algorithms use in one or the other way these combined properties. So mostly positive definiteness plus structure. And it's, of course, a bit more delicate when you have irregular samples, but also in this case, we have algorithms which work quite fine. Now, the next part, I hope it's visible here, is to show you that you can either do what you describe in frame theory, that somebody says, somebody is giving me a collection of vectors. And it's really, you should think of the columns or rows, in our case, the rows of a matrix. Nobody is prohibiting in such a system that you're having repetitious row number. I mean, in the general abstract situation, row number 5 and row number 20 could be the same. So this is why people also write, they call it a sequence of vectors, or they call it a labeled indexed family. So, well, I think it's very much like you describe the roots of a polynomial. In order to make sure that a complex polynomial has exactly n roots, you're counting multiplicities. So you would say, well, this is a triple root, so you write it 3 times, even if it's only one number where the polynomial is having a 0, but it's with multiplicity. So in the same way you have it here. So you have clearly labels automatically by having different rows, and you don't care whether they're equal or not. Okay, so the claim is in a operator norm that you would like to know whether these coefficients are the same as the, of course, more efficiently computed samples of the short-time Fourier transform. And that's the answer that you have here. If you do the comp norm command, you get one of these nice okays, so to say. So here you do really you're localizing your ongoing signal x with g taken to different positions. And then we take the Fourier transform but sampled at the multiples of b, which is 16 in our case. But in reality, we're taking a short FFT. We're saying we can do the same thing by kind of doing the basic period, and that's exactly the trick that I had with the periodic convolution trick. So you take the G, no, the localized part of X, which is not very long maybe, but you make it, reduce it to length A, and sorry, length N over B, because then you have exactly N over B coefficients of this short Fourier transform, and that's exactly what you would like to get. If we go from column number 5 to column number 6, each time we pick up exactly N over 16, that means 30 new coefficients, and the overall number is 720. Okay, so in terms of interpretation, what is the information that we have? These are the samples, or this is a bunch of vectors, and we get the scalar products. And the question is, how do you get from the scalar products to the vector? So now another way to tell you a little bit about my world of Gabor atoms, or Gabor theory in matrix analysis, is we could look at this family of lattices, the indices. You see here it starts with 1, 17, 33. So I'm going down the first column of my matrix describing the lattice. And these are the coordinates. After a while, I would jump to second column and so on. And I could take the full quasi-continuous short-time Fourier transform and sample it at these sampling points, and that would give me the same thing. So here it's actually a sequence with 720 entries. Here it's a rectangular matrix with height, which is, we have seen, we get 30 samples per column, and we have 24, but that's exactly the same number, and they're coming in the right order, and everything is fine. Now, this part here only shows you that I could do fast algorithms. Here I'm doing a sampling of the short-time Fourier transform, and I do a synthesis operator with the dual window, or I want to do a synthesis with the Gabor windows. So that's multiplying with the Gabor family, but I do it efficiently now, and I do I reconstruct, or I choose as coefficients the minimal norm coefficients, which are the samples of the short-term Fourier transform, and they are all giving us in a slightly different way, of course, numerically, in the sense of they're not exactly the same thing, but numerically, practically the same function up to numerical precision, we get the same thing. There's also a story of Nuhag, which there was one colleague, Mario Hampais, who was saying, well, our algorithm for STFT is much faster than the Gabor synthesis operator. But we're just doing adjoint operators, and one is multiplying with the Gabor matrix to synthesis, and the other is taking the joint, taking scalar products. So why can it be slower? There must be a way to improve it, and that actually he found a way to re-implement the original and old routine so that now they are both quite fast. So both of these routines, which are concatenated here, are working very well. And you see you need a GD, which you also can compute very efficiently. Now, the next thing that I would like to at least indicate to you is, because we are approaching the end of the course slowly, is what is a Gaba multiplier? Or actually, what is a short-time Fourier transform multiplier? That's my terminology. In the case of a Gauss function for continuous variables, it would be called an anti-big operator. Anti because of certain covariance properties, but we don't have to worry about this. So I'm saying, well, assume you have this, think of the beginning of our session today, this spectrogram, and there is some noise which you would like to eliminate. Well, then clearly you would like to multiply with something small or zero, which helps to eliminate this part of the phase space of your recording. You could also say you need to do some hearing, produce a hearing aid, which emphasizes the frequencies where my ear, the ear of a senior person, is not working well enough. And then, of course, you multiply in these frequencies, maybe not all the time, maybe only when somebody is speaking, whereas if it's just ordinary noise, a different moment in time, you would like to suppress the high frequency. So you have something, and that's just a picture on the right-hand side, which is supposed to be something which should not change too drastically. Sometimes in my talks, I present audio device. I mean, the device of an audio engineer who is having the sliders for different frequencies, pushing them up and down. So what I would put here in the vertical direction is that this is maybe in that direction here, I would say at this moment, I try to emphasize these frequencies very much and the rest is not very big. One also has to say that one has to be careful. This is only a complex valued function, which I think wasn't a good idea. Maybe I try to do it while I'm talking. So maybe I'm taking just the real part of this, but even then it might be not so good, because the problem is that we have, unlike with paintbrush, we have phase factors in the synthesis process, and therefore we have to be careful. Okay, now, so what is a Gaba multiplier? I'm jumping to this step here. It is a procedure where we are taking instead, well, let's see. Yeah, so the first thing is that if we would take a full short-term Fourier transform, and we only have to normalize it by the redundancy, and the redundancy, if A equal B equal 1, then the redundancy is n, because n divided by 1 times 1 is of course n. So that's the only thing I have to do in the synthesis process. I can take the same window for synthesis and analysis. This is the continuous inversion formula in the concrete setting of MATLAB. And then, of course, the comparison tells us we are fine, we are reconstructing it. Now we're saying, instead of just taking the short-term Fourier transform and recovering it, I would like to multiply it. So you see, before doing the synthesis, I'm multiplying with this symbol, and I'm getting a new function. Now the plot is probably still the old one, and I'm not sure how long it takes, but this is the idea of a Gaba multiplier. So you're saying, I would like to have a continuously changing position of my sliders of my audio pult. And okay, you see it here. And the remarkable thing is, that's now also has to be rerun, that after multiplying with the profile that was shown in the random figure, I should see that the synthesized signal is something which is, now I hope it comes, is having a different concentration. And at least what you can see here is the areas where you have significant contribution left over are exactly the areas where you have something like this. I'm not completely sure, but I think this seems to be this part here. The right part here seems to be this part here, and the lower part is the peak here. But again, I have to say, one has to be careful with the frequencies and so on. So maybe one should be careful with this. Now, so what is the same done now using what I call a Gaba multiplier? A Gaba multiplier is doing the same, thing with a sampled short-time Fourier transform. So I'm saying, I'm not willing to compute all these samples, go to extreme high redundancy, and then go back, but I would prefer to just do it on the samples. That's also meaningful only when you have a smooth symbol, otherwise samples at one location might be completely different from the other one, and that's why I was choosing this, this good thing. Now I can also check this here. Now, of course, we do not expect that everything is exact, but remember the signal was normalized. So this is a signal of norm 1. So when we see a difference between the Gaba multiplier and the STFT multiplier. So doing multiplication in the discrete or a continuous setting, they have almost the same norm, but the error is, well, you can say only or 13% roughly, or 14% or so. Now, I must say this depends very much on the density of the lattice. If I increase the density of the lattice, I would get something different. And the other thing which I was putting beforehand, or which I would like to mention once more, is this part here, the tight atom story. So here you see GT is the tight atom, is Gabor tight according to the method of Guido-Janssen. That's always the last two letters indicate the author or the idea, the inventor of the idea. And it is the following, that you're saying, I'm not playing the asymmetric game of inverting the frame operator and use it for either the coefficients or for the synthesis, but I try to do it in a symmetric way. Well, what does it mean? Instead of the square inverse of the Gabor operator, we take only the square root and attach it on both sides. So you see here, the tight atom is a fast algorithm giving you a certain function here. Maybe I'm trying this also to show you the G, the tight atom, and the dual atom. The idea is the dual atom is arising by taking the square root at the inverse frame operator, so it's further away from the original one than the square root, which is kind of halfway in the direction. So you see here, this is Gauss function. These were the dual windows. The tight ones are kind of much nicer in a way, also because they don't have this side bump or so. The side lobes are not as deep as they are here. So these are quite good guys. And they have the good properties if I form the corresponding Gabor family, or I could say a form that would be another routine. I would say I have a quick routine to compute the Gabor frame matrix. So it's Gab frame matrix. I hope that I have my right memory of this routine. Then I should get, maybe I'm making a section break here. Yeah, so I'm getting the same thing. You see here, it's computing those few sidediagonals which are potentially relevant. So we can also see here that if you take this function here and you take the square of this, that they would add up to 1. So that's one of the methods to create a bupu. Well, almost a bupu. It's not. Here it's almost a bupu. Okay, so now another thing which is probably all I can do before, instead of going into theory today, is to explain the concept of the time frequency representation of these vectors for these specific properties. So we have seen that every matrix, n by n matrix, can be seen as a superposition of time frequency shift matrices. And this is an extremely important basis to understand the behavior of time frequency shifts by conjugation. What does it mean? You're multiplying a random matrix. So here it's a random complex matrix of size n by an arbitrary time frequency shift. You can change it if you want, but I was choosing something so that you can recognize the time shift is 3, is different from the frequency shift. Both of them are relatively small or so. And so if I'm playing this game, I would say that these are unitary operators. That's quite clear because time shift doesn't change the length of a vector and multiplication with pure frequency either. But in a formal level, you would say a unitary matrix is a matrix where transpose conjugate of the matrix is the same as the inverse matrix. Okay, on the right-hand side, you see that everything is fine. Now, I'm doing a conjugation. So a random matrix R is multiplied from the left and from the right with the matrix, respectively, the inverse matrix. I admit that when I was doing the experiment, I realized it's better to first, I mean, to put the matrix to the right for my illustration and the other to the left also, and also you should mention that, of course, roughly speaking, the inverse is a -3, -5, but not exactly, because there is this commutation relationship. So there's a phase factor of the form relating to these shift and frequency parameters, only if I would take two numbers which are together a multiple of n. So for example, if I would take n equals a as a time shift by 20 and the frequency shift by n over a, which is 24, then I would see that there is no problem with the inversion. It would be exactly the negative one. Yeah, maybe I can insert it here. So just to tell you that I'm doing one more break. So if I would take TANA is time frequency shift matrix of format A and N over A, maybe like something like this. Well, I'm not sure. No, I can only, maybe I'm doing a time shift by A, yeah. And I do modulation B by N over B is a frequency shift by, now, well, it's not NAA, so to say. I'm doing a frequency shift by N over A, so that would be the right thing. And now I would ask, what is the product? Do they commute? Tana times MNRR or MNRR with Tana. And the result should be yes, they commute. If I didn't make a typo, of course, I have a typo. Yeah, so it was just a typo. And in this case, also the inverse of time. Yeah, okay. This was TFANR is time frequency shift matrix of NA and N over A. So that would be the combination of these two operators. And I would say, well, why not take the time frequency matrix shift operator in the negative direction, so minus N over A, or I would take the inverse of this TF. And then I think we should see also that in this case, you see another nice display. So if time and frequency shift operators commute, the inverse is just this. Otherwise, you would check that you get phase factors. But that's not the point of my story. The point is that I would like to look what is the effect of this conjugation. Just remember that one way to look at the Gabor frame operator is that you would say, I have a collection of atoms. They're living at near certain lattice points. And we are projecting our signal into all these atoms. So that's essentially how you can understand the Gabor frame operator. But the different or equivalent viewpoint is that you're saying, no, instead of projecting onto atom at a certain location, we move in the time frequency shift manner our signal, our spectrogram, so that everything is put at the center. We project afterwards and then we go back. And you see here is a shift moving our signal and our area of lattice point to the center, then doing the projection and then moving everything back. That's something that was interesting. Okay, now what I wanted to do with this plot here is to demonstrate what happens, what is the effect of the matrix in the spreading representation. So we have the matrix R, which is a random matrix, and it works only well for random matrices, this simple experiment. And we have a certain pattern. We don't care for it. We do this conjugate operator. So we have moved it around. And then we look at the quotient. Now the comp-IMRI means I'm comparing two images, namely the real and the imaginary part of the quotient. And what we see is quite amazing. It looks like a plane wave. So the question would be, well, if it's true, and of course you can sit down and compute it, that the formula with this spreading representation is using the time frequency shift operators, and going through this process, you find out it's really true that if I would change from 3, 5 to 7, 12, you would see other patterns, and you would kind of get the feeling that each time you're doing such a conjugation with the time frequency shift operator with certain parameters, you're getting a plane wave which has corresponding features. So, well, if my guess is that the quotient Q is a pure frequency, I would like to go to the inverse Fourier transform domain, because a plane wave is a pure frequency in two variables, is a unit vector. So I'm doing the inverse Fourier transform of my quotient. And I find if I do a spy command and I don't see anything, I zoom in very strongly. So you see, okay, that looks quite nice. It might be something like 5, which is halfway between 0 and 10, and it might be something like 3. But our shift parameter was 3, 5 was 3 in the time direction and 5 in the frequency direction. So somehow it seems to be wrong. The time parameter was the small guy, and both were positive. So I would expect that we should see everything here at the position 3 to the right and 5 down. So how can we make sure that this quotient is done in the right way? And the idea is to introduce the so-called symplectic Fourier transform. I will try to come to an end soon, but there's still something to be explained. Now, the first thing is to recall what is the two-dimensional Fourier transform. We develop the Fourier matrix, the matrix describing the discrete Fourier transform. And we find out that the two-dimensional Fourier transform is exactly the same thing, again, numerically, up to numerical precision, as the multiplication from left and right. Now, if we write the symbol FRF, MATLAB interpreting it as associative law, it says, first I have to compute F with R. So I'm doing a Fourier transform on the columns. Once this is computed, I'm doing this from the right, but the Fourier matrix is a symmetric matrix, so it's multiplying with the transpose from the right is doing it on row vectors. So essentially, from this formula, you see you can put brackets wherever you want. It will be the same. You do both row and column-wise inversion, a Fourier transform. Now, the inverse, of course, is the same as doing it with the transpose conjugate, which is the same as just the conjugate, and that's the inverse Fourier transform, just to check this. Now, the symplectic Fourier transform is just, I have taken here the two-dimensional inverse Fourier transform, but then I had to do some corrections. So instead of changing the role from positive and negative, I should take one inverse Fourier transform, one forward transform, and we also have seen instead of 5 and 3, we got 3 and 5, we were getting 5 and 3. So what you can do is you can take an inverse Fourier transform on the columns. Then you take on the right a row-wise forward Fourier transform. We know that each of them is producing a factor of the square root of n. So we want to have something which is unitary, so we divide by n. And then we also change the order of rows and column. And all these things are harmless modifications of the short-term Fourier transform. And it turns out that if you're looking at this symplectic Fourier transform, you can, that's just convincing you an example, that the Euclidean norm of the random matrix, which was normalized, or its Frobenius norm, or the square root of the trace, which is the Hilbert-Schmidt norm, or the same with the symplectic Fourier transform is the same. Now, actually, I should have inserted the picture with the symplectic Fourier transform and the SPI command, and you would have found that it's in the right position. So the conclusion of this part is, well, sometimes it may be interesting to not look at the spreading representation, which has this effect that conjugation with time frequency shifts is giving you a multiplication with plane waves, but we would like to translate this multiplication with pure frequencies into an ordinary translation. So we take the symplectic Fourier transform of the spreading function of our random matrix, and we find out on the right-hand side, you see it's numerically the same as the so-called Kkohn Nirenberg symbol. So the Kkohn Nirenberg symbol is quite valuable to discuss, let's say, slowly varying systems. So they are like convolution operators, blurring operators in image processing, which are not constant moving averages, but with slowly changing profile. So you can think of something like, well, it's a Fourier transform of the current kernel, but the kernels are allowed to change and so on. And it's true that if the system is a slowly changing system, then its spreading function is very well concentrated. That's terminology I learned from Werner Kotzek, who is an engineer, who came from the communications theory department, that he told me that underspread operators are the ones suitable to model mobile channels. And instead of doing the spreading representation, which I tried to explain today, we can take its symplectic Fourier transform, which is the symplectic Fourier transform, or called the Kkohn Nirenberg symbol. Now, we also know that an operator which is highly concentrated, a function is very concentrated, has a very smooth Fourier transform. And the same thing is here. You get a very smooth Kkohn Nirenberg symbol, and just remember, if somebody has the identity operator, you would say it's just the main diagonal. And I would say, no, the Fourier coefficient is just one Fourier coefficient. It's extremely well concentrated. In the spreading domain, it's just a single one at one position. What is the Kkohn Nirenberg symbol of the identity operator? It's just constant one. Okay, now these two formulas just tell you that my code that I'm using to convert from matrix representation to Kkohn Nirenberg and back, and also in the opposite direction, are kind of inverse to each other, and that the symplectic Fourier transform is idempotent, it's an involution on these matrices. So they are non-preserving, and once you are doing it twice, a pair of a forward and an inverse Fourier transform come together, and you do it in such a way that if you start with the tensor product, G with F, I mean, essentially you map F tensor G hat to G hat tensor F. You switch the role, and if you do the same trick twice, everything is fine. Now, here I'm just verifying that the spreading operator and the Kkohn Nirenberg symbol are inverse to each other. And what I don't display, I mean, what I don't compute in detail, but at least wanted to mention is this effect in the Kkohn Nirenberg symbol. Yeah, I mean, this is a short demo what a rotation of rows and columns is doing. So here I take my standard matrix and I rotate and move my 1, which was in the left upper corner, by 1, 2, 3 columns to the right and 2 columns down. So this is a rotation of rows and column by 2. I'm first calling the rows and then the columns. And so what you can see here is if I take the Kkohn Nirenberg symbol of my original random matrix, that's the RKN. I can either take this Kkohn Nirenberg symbol and move it around by rows and columns. And in the same way, I can take the Kkohn Nirenberg symbol of this modified by conjugation and this is exactly the same. So I think it's time to stop for today, but I will make the code available and you can study the rest. And the main point might be that we have to do this in abstract settings so that you're getting at least a first understanding of both a spreading function and the Kkohn Nirenberg symbol, and actually how the Banach-Gelfand triple situation can be used. Okay, yes, maybe one little thing I should mention. If you start with a lattice, so in our case it was this this oblique lattice or the original lattice or so, then you can expect that the two-dimensional Fourier transform of the lattice is just another Dirac comp, while of course up to the amplitude, which is the number of lattice points. Now in the symplectic case, the same is true. So also the symplectic Fourier transform of a Dirac comp of a subgroup is a Dirac comp of another subgroup. I have called it llama for adjoint lattice, lambda adjoint. And the code is also adjoint lattice, which uses actually the symplectic Fourier transform. And the interesting fact is, if you're giving me any lattice, then certain time frequency shift operators commute with those which are the given ones generating my lattice. And it turns out these are exactly the ones which you have here. In the theory of Fourier series, you have the same thing. You have the Fourier transform with a continuous range of variables, and there are only few which are compatible with periodic functions. So the Fourier series expansion says you need only frequencies which are having the same period to expand it. Now we have something for operators. An operator which is periodic in the sense of invariant under certain time frequency shifts by conjugation must have a spreading function which is concentrated on a lattice, and it's exactly this adjoint lattice which plays the role now of the orthogonal lattice. So the adjoint lattice is more or less take the orthogonal lattice, but switch the time and frequency variables. That's a good first understanding of this adjoint lattice, and it has a big relevance for the rest of the understanding of Gabor expansions and time frequency shift operators, slowly varying channels, and so on. Thank you for your attention.